Imagine standing at the edge of an active caldera at night. The heat is overwhelming, the air thick with an unbearable, choking stench. It feels entirely hostile. Yet hidden within this poisonous exhaust is an element that makes biological life possible. To understand why, we have to look back billions of years. Earth's early crust was a chaotic expanse of constant eruptions, bleeding element 16, sulfur, out from deep within the planetary mantle. As these massive emissions vented into the sky, they reacted with the raw atmosphere, settling into the rocks and oceans to establish the chemical foundations of our world. Without this violent, toxic beginning, the molecular makeup of our planet would be completely unrecognizable today. When isolated into its pure physical form, sulfur is surprisingly beautiful. It crystallizes into striking golden yellow formations that betray its turbulent origins. It is highly reactive, melting with very little heat and igniting to reveal a haunting pale blue flame. That combustion is responsible for a persistent myth. Pure sulfur actually has no scent at all. The famous rotting odor only occurs when it burns and binds with oxygen to create sulfur dioxide gas. The pungent gases often associated with volcanoes are a chemical byproduct of this reactivity, creating a sharp contrast between sulfur's physical beauty and its reputation as a pollutant. To see its true value, we must leave the geological scale and dive deep into the microscopic machinery of the human body. Here, this supposedly toxic mineral is an absolute necessity. Every single cell you possess requires sulfur to survive. It acts as the backbone for two specific amino acids, cysteine and methionine. These are the primary scaffolding blocks for human biology. Because of its unique atomic structure, sulfur atoms reach out and lock tightly onto one another, forging strong, resilient chemical bridges. These microscopic links translate directly into macrophysical strength. They give your skin its elasticity, hold your hair and nails together, and actively repair damaged tissue. Even crucial metabolic hormones like insulin rely entirely on these specific sulfur bonds to maintain their correct shape and regulate your blood sugar. Every structural protein and metabolic hormone mentioned here relies on these sulfur bridges to maintain its physical form. Beyond biology, humanity eventually learned to extract and manipulate sulfur's high reactivity for technological ends. Early apothecaries ground it into medicinal treatments. Later, military engineers harnessed its combustibility to invent gunpowder, while industrialists used it to harden rubber for the tires of the first automobiles. Today, the majority of extracted sulfur is converted into a single, indispensable compound, sulfuric acid. In manufacturing, it is the king of industrial chemicals. It acts as a hidden solvent, processing the raw phosphates that become agricultural fertilizers. Without it, modern crop yields would plummet. It is also deeply embedded in our future technologies, required to refine the metals and manufacture the high-capacity batteries that store modern power. Take away sulfuric acid, and the electrical grids, transportation networks, and food supply chains of modern society would grind to an immediate halt. But utilizing this element on a mass scale exacts a heavy toll. Burning the sulfur-rich fossil fuels that power these factories releases millions of tons of sulfur dioxide into the air. Once airborne, the gas mixes with atmospheric moisture, altering the chemistry of the clouds to fall back down as acid rain. It strips nutrients from forest soils, acidifies vulnerable river ecosystems, and severely aggravates human lung conditions. To mitigate this crisis, engineers now install massive, advanced chemical scrubbers inside smokestacks, capturing the toxic exhaust long before it can reach the sky. Modern industry exists in a constant state of tension, trying to harness the benefits of chemical progress while suppressing its destructive tendencies. This delicate balance isn't confined to our home planet. Planetary geologists have tracked the signature of element 16 deep into the solar system. We have detected vast sulfur deposits across the rusted dunes of Mars and traced its compounds along the frozen, fractured shell of Jupiter's moon, Europa. But nowhere is it more prominent than on Jupiter's moon, Io. It is the most hyperactive volcanic body known to science. Driven by extreme tidal forces, Io constantly turns itself inside out, painting its surface in reds and yellows with continuous sulfur eruptions. From the microscopic bonds inside a human cell to the volcanic plains of distant moons, sulfur is a persistent component in the physical organization of matter. Next time, we encounter element 17, chlorine, a highly volatile and entirely distinct chapter in the story of chemistry. Follow the Atomic 118 channel as we continue exploring the hidden forces that shape matter.